Our next unit is a bit of a hodgepodge. It's not about any one thing. It's about a group of things that have a particular feature in common, like this. I was thinking about putting hanging the bowling ball up again, but I don't have to. Here, the electrical cable hangs from the ceiling and it swings back and forth. It's what we call a pendulum. Everybody's aware of that. Now, as the thing swings back and forth, it has position, velocity, acceleration. It has gravitational potential energy. It has kinetic energy. It's got all the physics going on that we've talked about so far. All that physics right there. But it has one characteristic that distinguishes it from everything else that we've studied so far. And that is the fact that the motion repeats itself. The thing doesn't end up on the other side of the room. It stays generally in this area, and it goes back and forth and back and forth. This is a special kind of motion called periodic motion. There are many, many more examples. If I just think of a wheel on a car, if I mark a position on it, maybe I take a brightly colored sticker and put it on there, it goes around and around and around, repeating that motion over and over again. I can take a mast and hang it on the end of a spring, and it bobs up and down with the motion repeating. The planets go around the sun, and they repeat. For example, in 365 days, happy birthday. Motion that repeats is called periodic motion. And that is our new issue of study here. Periodic motion repeats in time. I'm being specific about the repeating in time bit because we're also going to encounter some motions that repeat in space as well as time. One complete motion is called a cycle. Back to my pendulum here. One cycle of the pendulum motion is starting here, swinging away and back again. The full motion, starting with some initial position and repeating, coming back to the initial position again, that's called one complete cycle of the motion. Today's discussion is really about terminology more than anything else. The time it takes for one complete cycle is called the period of the motion. I might reflexively from time to time say the time period of the motion. But to say the time period is a little bit redundant because the term period refers to a specific amount of time, the time required for one cycle of the motion. So if I'm to calculate the time period, I'm talking about a certain number of seconds that pass per cycle. And that's what I mean by definition, the time period. The time period is a certain number of time, or certain measurement of time, a certain measurement of time divided by the number of cycles that happen. For example, I could take a stopwatch and set my pendulum swinging and count 10 cycles of the oscillation as the stopwatch runs. After 10 cycles, I then hit the stopwatch button and I get lowercase t, the time that I record off my stopwatch. Then dividing by the number of cycles would give me the time period in second. It wouldn't be a terrible crime if I wrote down seconds per cycle. But cycle isn't a unit. It's not a dimensional quantity. It's not a measured quantity. It's counting. A cycle is just a number that doesn't have any units at all. So the units of the time period are seconds. For example, if I time a thing and it takes 35 seconds, or time this, and say it takes 35 seconds to do 10 swings, the time period of that motion would be 3.5 seconds. I hope you feel that that is completely obvious and straightforward. The period is used to describe the timing of periodic motion. So since I'm going to spend the rest of our unit studying periodic motion, the time period is going to give me a way of describing its behavior in time. There's a little bit of a sticky wicket here in that this is not the only way we describe the timing of periodic motion. We can also describe periodic motion in terms of the frequency. The frequency is the reciprocal of the period. What the math folks mean by reciprocal is 1 over. Sometimes we call that the inverse. I'm not comfortable with using that math term in this context. So I'll use the very fancy word reciprocal, meaning that the frequency is not seconds over cycles, but cycles over seconds. It's the reciprocal of that quantity is the frequency, and so it's the number of cycles that happen in 1 second. So the frequency, there's a simple relationship. The frequency is equal to 1 over the time period, and therefore it has to be true that the time period is equal to 1 over the frequency. Since the time period is measured in seconds, then the units of frequency are 1 over seconds. 1 over seconds isn't terribly convenient to look at or to write. And sometimes we write this as seconds to the minus 1, which would be equivalent. But this unit gets its own name. It's called the hertz. And the hertz, H-E-R-T-Z, gets abbreviated H-Z. Frequency measured in hertz. You might wonder, if I'm going to use the period to describe the timing of periodic motion, and I'm going to use the frequency to describe the timing of periodic motion, why do I have two ways of saying what's basically the same thing? I'm not sure how it's useful if the frequency is 1 over the time period and the time period is 1 over the frequency. That's not a big difference between the two. Well, the reason why it exists, roughly, not exactly, but we generally use the period to describe things that happen slowly. Now, slowly is not a precise statement, sort of relative language there. Period is used for things that happen slowly. For example, we often talk about the motion of a pendulum in terms of its period in seconds. And that's not really surprising because pendulums were used in early clocks as the mechanism to create regular intervals of time to move the hands around the face of the clock. So pendulums are measured in seconds, and we describe them in terms of their time period. Satellites in orbit around the Earth, for example, the International Space Station, which is sadly coming to the end of its useful life, orbits the Earth with a period of about 93 minutes. Takes the International Space Station 93 minutes to do one complete lap of the Earth. And of course, the orbits of planets are described in terms of their time periods in days. Most notably, it takes the Earth 365 days to orbit the Sun. These are all examples of period, and some of them, particularly the time periods of planets, are quite long indeed. We use frequency to describe things that happen very rapidly. For example, an engine combusts gasoline to convert that energy, that chemical energy, into rotational motion, the spinny bits inside the vehicle. And some of us have cars that have a speedometer, of course, all cars have that, but also a gauge that measures the RPM. RPM actually stands for revolutions per minute. So it's not our SI unit for frequency, which would be revolutions per second, or cycles per second. It does it in a minute, but it's about 2,000. In the course of 60 seconds, the engine rotates about 2,000 times. And so it has more revolutions than seconds. And so we generally describe the rotation of an engine in terms of its frequency. Radio waves, when you tune into a radio station, we still do that. A lot of times we just plug our smart device into the car and play whatever's on the playlist. But if I tune the radio to sports radio 94 WIP, right, in Philadelphia for our international listeners, that 94 is 94 megahertz. The vibrations of electromagnetic waves, and we're going to study those, the vibrations of electromagnetic waves are described in the context of hertz, and because they have a very high frequency indeed, in the context of megahertz. Musical notes. Musical notes, whether they're made by a person's voice, or a stringed instrument, or a wind instrument, or even an electronic instrument, sound and music are vibrations. A very common note in music is the A note, also happens to be the note of a dial tone on a telephone. That's 440 hertz is the frequency of oscillation of an A note, 440 hertz. It vibrates many more times than the unit of time, the second. And so frequency being used to measure things or to describe things that happen very fast. You might lament this a little bit. In fact, I know that you're going to. I'm going to ask you, please, as a personal favor to me, suspend some disbelief here. I'm going to spend the rest of our time together talking about a little bit of math. It's almost certainly a bit of math that you despised when you did it. I hear students lament all the time, even though it's none of my business, about the unit circle. Oh God, someone decries. I'm only going to talk about it as much as I need it. And I need it very, very badly. So despite the fact that this description I'm about to give is a very simple one, it is critically important. For our success in this unit of our physics, we're going to need this to be coldly understood. We have to be, as they say, locked in on this. The length of a circular arc is proportional to the radius of the circle and the angle subtended. What a bunch of fancy words. What I mean is this equation, where S, you can see here on my diagram, is length along the arc. Not all the way around, just this bit here. As I imagine, and I will imagine in the future, maybe this is a mass tied to a string that's going around, or a planet in orbit that's going around thus, and it travels a certain distance s. I know it's strange using s for distance, but the math folks like to do that. And this is to a certain extent their equation, although we all love it very dearly. S is the length of the arc, and that would be measured a certain number of meters. It would be tricky. I would need a flexible measuring device to measure how many meters that is along the arc. But then that number of meters is equal to the radius of the circle, which would also be in meters, multiplied by the angle. This is called the arc length formula, and I love it. I can't live without it. In physics, it is automatic, it is ubiquitous, it is powerful. I really need that equation to be true. But it's got a problem that's built into it, you see? Because if I go all the way around the circle, just to test this equation, if I go all the way around the circle, then surely the distance s that I go is the full circumference of the circle, 2 pi r, which would mean that for going all the way around the circle, 2 pi r is equal to r times theta. Well, here's the problem. I have an r on each side, which cancels. And what I'm left with is the bizarre statement that the angle all the way around the circle is 2 pi. The reason why that offends you is because you know that the angle all the way around the circle is 360 degrees. Everybody knows that. But 360 is not, or 360 times the radius, is not the circumference of my circle. It doesn't work out. And I really need this equation to work out. I need this equation to be true. In order to make the math simple, I need this equation to be true. So what I do is I say there's a new kind of angle measure. It's called radian measure. And while it is still true that there are 360 degrees in a circle, there are 2 pi radians in a circle. 2 pi radians in a circle. And I know that causes all sorts of trouble because you have to start thinking about angles differently. Instead of thinking about 45 degrees, you have to start calling that pi on 4. And instead of calling it 60 degrees, you have to call it pi on 3. And instead of calling it 30 degrees, you have to call it pi on 6. I know, it's a struggle. But you use it enough and you can, in fact, memorize it, which they tried to do, force you to memorize the whole thing. But this is why it exists. I've had students ask me in the past, why do they even do the radian measure? It's crazy. It's just math nonsense for no reason. No, it's got a very good reason. I need this to be true. I need the arc length formula. Here's another thing. The radius is measured in meters, and the radius is measured in meters. So 2 pi and theta can have no units at all. If s is measured in meters, in the arc length formula here, if s is measured in meters, and r is measured in meters, then to make this equation dimensionally consistent, theta can have no units at all. Now, a bad habit that we have, sort of unavoidable though, is referring to radian measure as rad. For example, someone might say that 90 degrees is pi divided by 2 rad. And it makes it seem like rad has the same status as seconds and meters and joules. It doesn't. Rad is not a unit. And I'm going to emphasize that a little bit more here. Here's my diagram again, but I'm putting numbers to this just so I can get a handle on what I'm talking about. It seems to me, when I look at this circle, that the angle subtended here is about 1/6 of the full way around. you can imagine pi slice, pi slice, pi slice. There's 3, it gets me halfway. And another 3 gets me all the way around. That means 6 pi slices all the way around. It means that as this diagram is drawn, that angle subtended seems to be about 1/6 of all the way around the circle. Well, since all the way around the circle is 2 pi radians, there's 2 pi radians in a circle, divided by 6, that's pi on 3 radians, which you know as 60 degrees. But 60 degrees doesn't do me any good. I need it in radians. I just have to get comfortable with the idea that that angle is pi on 3. And that's totally okay. There's nothing wrong with that. I've suggested here on my circle that the radius of the circle is 5 meters. The radius of the circle is 5 meters. Well, now I can calculate some stuff. I can use the arc length formula and calculate the distance along the arc here. Using the arc length formula, S is equal to R times theta. Well, R is 5 meters times pi on 3 rad. Now, I've written the rad there because if I were to say it out loud, I would probably say pi on 3 radians. That's probably what I would say when I spoke it. But when I do the calculation, I'm doing 5 times pi on 3, which is 5/3 of pi, and I put that into my calculator as 5.23 meters. 5.23 meters. Where did the rad go? You lost the rad. The rad was never there. Because radians are not a unit of measure. They're just a tag. It's just a tag to say, hey, look, I'm using radian measure. You might say, well, doesn't the pi give it away? There's a pi there. So once the pi's get involved, you know you're doing radians. Well, it turns out the pi doesn't have to be there. I could take that 3.14 and divide by 3, and then it would be that decimal of rads. I could do that. And so the pi is not good enough. Rad is not a unit. It's just a tag that I put on that gives you the heads up that I'm using radian measure. So this is going to be a little bit of a struggle, I know, but I've only presented you with what we need to know, and I've left out a lot of the interesting stuff that the math folks like to talk about, because that's their business down there. Gives them something to do.